Konnichiwa, irashaimase, welcome back, y'all. In this video, we're going to talk about circuit elements. Specifically, we're going to start really honing in on what a circuit element is and how it works. Let's begin with the following definition. We say that a circuit element, sometimes called simply an element, is any electrical object with two or more wires sticking out. Those wires are called leads. In some situation, we also call elements branches, as in different branches of a circuit. These are the fundamental building blocks of all circuits and thus form the foundation for circuit analysis. In our work together, we're going to think about circuit elements as coming in three forms or three flavors. The one that is most useful from the applied standpoint is real elements, things that you can touch and feel. So for example, here's a set of real resistors. I can touch those, I can connect them. Those are 4-band resistors. Here I've got 5-band resistors. Very, very beautiful things that I can touch and feel. They come part of the electric laboratory kit. Here we've got a real DC voltage source that connects to a 9-volt battery, and we've got a real DC current source. We will see that real components form the basis of all the work that we do. The next set of elements that we're going to think about are called digital elements. Digital elements are computer models of real elements that usually come in libraries available in many computer-aided design software. So for example, there's software that we saw, in this case called Fritzing. I use that because it's cheap and well done. There's also called Autodesk Eagle. We'll take a look at that in a second. Express PCB or Altium. These software programs are written by engineers and designed to simulate the behavior of circuit and expedite, make faster design and testing. Let's take a look at what I mean by digital elements. In this case, let's go ahead and just type in Express PCB. This is software that's used to design printed circuit boards. PCB means printed circuit boards. Here we can kind of look through the images and check that out. On the right, we have an actual circuit, and on the left, we have a digital representation of the circuit board in the software Express PCB. Let's take a look at another one called Altium Designer. These are very, very sophisticated tools that allow electrical engineers to completely simulate many aspects: the size, the layout, the way that electrical connectivity should come, the electrical behavior. One of the things that we're developing in the linear algebraic nodal analysis is an algorithm that gets fed into these computer-aided design softwares so that when engineers want to test and they say, okay, I'm going to push this button, see how the circuit works, in the back of that button are a bunch of math algorithms that are basically saying, hey, you said that you wanted your circuit to do this. This is what our simulation tells us. Go iterate if you feel that some of the results are not what you want. In any case, when we're thinking about digital elements, think about it this way. We have a real element up top, and then the digital element is a representation of that real circuit element that can be used to simulate and test a specific design that an engineer might want in computer-aided design software. The last type of elements that we're going to talk about are called ideal elements, and those are mathematical models of circuit components. We use ideal elements to draw ideal circuit schematics, and this is at the very, very beginning, usually, of the design process. If we were thinking about this in terms of the construction of an automobile, we might think about an ideal element as a paper and pencil drawing or sketch of what the car should look like. A digital element would be a computer graphics rendering of all of the different components of that car, how they fit together, and then testing on a computer how we think it will run. And then the real element would be the car constructed in real life. For the work that we do to develop the linear algebraic nodal analysis, we're going to focus heavily on real elements and ideal elements. Real elements in the use of our laboratory equipment to test all of the theory and ideas that we're developing, and then ideal elements in order to develop the mathematical representation of those real elements that we're going to use in our model. With that in mind, in this video, we're going to focus heavily on ideal elements because there's a lot going on there. For ideal circuit elements, we're going to focus on a couple of properties, specifically 2 of them. The first property that we're going to look at is called a circuit schematic, or a stylized sketch that represents the element in the design process. When electrical engineers are designing circuits, they actually break those circuits into small components and then build larger circuits from smaller components. The most basic ideal circuit element is called an ideal element. It's the smallest one that we can use, and we'll take a look at a general template. So specifically, we say that a general ideal element when we're looking at the schematic or the stylized sketch is going to look like this. So it has a lead, a body, and a lead. We usually reference with a particular label, and then these two things are called terminals. We'll return to that in just a minute. But the idea is that we then can combine a bunch of elements that look like this into a larger circuit. And if the electrical engineer knows what she's talking about, that circuit will function to solve some real world problem. So first feature of an ideal circuit element is called a schematic or a sketch. The second feature that we're going to look at is called a mathematical model. So not only can we sketch these things, but underneath we actually have a mathematical representation in terms of equations of how this element is going to behave when we connect it to a circuit. Specifically, we say the mathematical model is actually a set of equations. They could be algebraic, differential, or logical, to explain how voltage versus current works. We saw that we had two variables for every element. And when we relate those two variables together, how does voltage work? How does current work? This starts to govern how those elements interact or behave when we connect them to larger circuits. In addition to the voltage and current connection, we might also have something called the time function that describes that behavior. So voltage in terms of time or current in terms of time. These models usually come from scientifically observing and testing real circuit elements over a long period of time and controlling many factors through the manufacturing process. Once again, every ideal circuit element, we're going to think of having an ideal schematic, a single ideal element, a drawing of what that means, and then also a set of mathematical equations that govern what that thing does when we connect it to other elements in a circuit. Let's dive into this ideal sketch to figure out all the stuff going on here. When we're doing our stylized sketch for an ideal circuit element, we're going to have a collection of properties that we want to highlight. First thing that we're going to highlight is that lead, body, lead. In this case, the leads are just lines that represent wires. So this is going to be a two lead element. I have one lead up here and the other lead down there. I like to use the words top and bottom if I'm referring to an actual schematic, looking at the top and the bottom, but it doesn't really matter. Just call the lead a lead. In between those leads, we're going to say the element body sits. So in green here, we see this is the element body. In purple, we see that this is the top lead. In yellow, we see that this is the bottom lead. The actual shape and look of the element body depends on the type of element that we connect, and we'll see that in just a minute. Next to each element body, we're going to put an element label, and right now we're using the variable X because this is not a specific type of circuit element. It's not a resistor, it's not a voltage source, it's not a current source. It's just a kind of a canonical template for what this looks like. The actual letters that we'll use to represent the element label will depend on the element type. So in this whole modeling paradigm, we're only going to use three types of elements. Resistors. The letter code that we're going to use for the element is going to be R for resistors. Voltage sources. If we were to label voltage sources, we would use the letter V. Lastly, if we label current sources, we're going to use the letter I. So if we don't have a specific element type, we might just say the canonical label is X. Finally, the little black dots at the end of the leads are going to be called terminals. This is where the actual physical connection between the elements is made. If we look at our real circuit elements, notice that this element, if I were to actually connect it to a breadboard, only touches the breadboard where these wires are sticking out. That's represented by a black dot in the canonical form. In the next video, we're going to talk about circuit nodes, and there's a different use of black dots in circuit nodes. But just know that when you see a black dot in an ideal schematic, it just means like that's where we're going to connect that thing in a larger circuit if we were to do it. Just to recap, when we're thinking about ideal circuit elements, we think about them having two components. First one was called the ideal schematic or ideal sketch. We just talked about all the features that we look for in ideal sketches for each element. Next one was called a mathematical model. We're not going to go deep into the mathematical model construction in this video, but what we will do is start talking about the type of variables that are useful in that mathematical model. Specifically, for each circuit element, we're going to assign two variables along with that element. The first is going to be the voltage drop across the element, which means that we take the positive lead of a multimeter, put it on one end, the negative lead, put it on the other end, capture how much voltage potential difference are on those two leads. That variable we're going to call the voltage drop across. We also have the second mathematical variable, which we're going to call the current running through. We can snip these leads, insert the ammeter in between, watch how current runs through. For each of those measurements, as we discussed before, we define what we call a reference direction, which in this case, we're going to do red and black to represent positive and negative. We could just do that in black. The moment I put a positive there, we know which side of the positive should be on, which side the negative should be on. Anytime we define the voltage drop across or current running through, we need to define what it means for that measurement to be positive and what it means for that measurement to be negative. In this case, if I get a positive reading, it means that the actual voltage drop goes from positive to negative. If I get a negative reading, it means the physical voltage drop that's happening in that current is in reverse. In our work together, I'm unique in this way. I will always define the positive reference current from the positive to the negative for the reference voltage drop. That is going to be a habit that runs through all of our modeling. To repeat again, every ideal circuit element, we're going to think about having two different sets of features that are really important. The first is an ideal schematic, a sketch of the element that we can use to design circuits. And the second is going to be a set of mathematical equations that models the behavior of that element when we connect it to other circuit elements. We said that the canonical form will have a sketch with a bunch of features and then two variables. In our case, the circuit elements we're going to use in this modeling will look like this. So this is an ideal resistor. Notice that when we label the voltage across that resistor, we use a subscript R to say, hey, this is a voltage drop across a resistor. Same thing, the current running through that resistor, I sub R says, hey, that is a current running through that resistor. We will also enumerate elements within their type. So we'll have like R1, R2, R3, and you've kind of seen that already. Let's go over here. This is a voltage source where we label it with V. When we say V sub V, that means the voltage drop across the voltage source. These will be constant. In particular, the engineering team that built this designed it so that that value is known beforehand, and we want it to be close to 5 volts. Here we see the current running through the voltage source, which we could tell because it says I sub V. Lastly, we see that here is an ideal current source. We label it with I. We define the voltage drop across that source. We know that that was a voltage drop across a current source because the subscript says I on it. Here, the current running through that source is from positive to negative. In this situation, the value of that current running through will be constant and defined by 2.5 milliamps ideally. This circuit is designed in such a way to give us known constants. The goal of our mathematical modeling process will be, once we connect all of these things, for the unknown variables, for the unknown values, so the current running through the voltage sources, the voltage across the current sources, and then both the voltage drop and current running through resistors, can we simulate the entire behavior of every element, only knowing how is the circuit connected and these values from the sources. Linear algebraic nodal analysis allows us to do that based primarily on linear algebraic structures. That concludes a more in-depth introduction of what a circuit element is. In the next video, we're going to talk about the nodes of a circuit and get real formal about it. I'll see you there.